F net is equal to MA. The net force that acts on an object will cause the object to accelerate. The acceleration is directly proportional to the net force and inversely proportional to the mass. But this is the equation we're getting to. Okay. Now, acceleration. What is acceleration? The rate of change in velocity. So it's Vf minus Vi over delta t. Got it? Okay. Now, if I put the equation for A into that place for acceleration in the equation of Newton's second law, F net becomes mass times Vf minus Vi over delta t. And if I do my mathematics correctly, this is mass times Vf minus mass times Vi over delta t. I hate fractions, so F net delta t equals, now what is mass times Vf minus mass times Vi? Change in momentum. Are you with me?
Yes, ma'am.
So, I can say, in other words, I can say the net force acting on an object equals the rate of change in momentum. This is another way of stating Newton's second law in terms of momentum. Newton's second law in terms of momentum. The net force on an object equals the rate of change in momentum. Okay, and this is impulse. Impulse is the product of the net force acting on an object and the time that this force acts on the object. Please don't copy this part because you've got it there. It's just mine. So the quantity of impulse would be equal to the quantity of change in momentum. The quantity of impulse. Impulse is that thing that is in the block. Okay? It's a new thing. That amount, that product between time and net force is called impulse.
So, in simple...
And the amount of impulse would be equal to the amount of change in momentum.
So basically, in simple words, it's like the duration of the force.
The longer the duration of the force, the bigger the impulse.
Okay. So the reason why we say F net times the time equal to momentum, because it is equal to each other. So F net times the time itself is impulse, and then the delta itself is moments.
I can do another experiment. Maybe I can involve you. I just don't have a bat, so you'll have to be the bat with the hand. You're going to equal it. I don't have a bat. If you want to look, I'm going to demonstrate it. We're going to play hand tennis now. First, I just want you to do this. Okay? But you'll now have to. Okay, so it went there. Now I want you to hit it. Okay? Try again. Look. You see, it went much further now. Why did it go much further? Because your impulse, you applied the same force. You can't hit it like. You applied the same force, but here you just did this. Okay, let's try again. And then, so first just like this, and then carry it on your hand. Okay, so it went there, which is not too far from you. And now, thanks for my glasses.
I'm so sorry. I'm so sorry, but
It's okay, it's not broken.
I'm so sorry.
Okay.
Okay,
So you get it.
Yes, ma'am.
If you have, I can do this. I can do this. And or if I want to really throw the ball far, I have to apply my net force for a longer time. Look here. Went there. Now I'm going to apply the same force but for a longer time. So that increases the impulse, the effect I have on this ball's motion.
Yes.
The longer the time of the net force acting on the object, the bigger the change in momentum will be, or the bigger the impulse will be.
So the F net stays the same.
If F net stays the same, you can make the impulse bigger by making the time bigger. Are you with me?
Yes, ma'am.
Everybody with me?
Yes, ma'am.
Alright. So the common concept of impulse is a new one. Right, let's do some more maths.
Yay.
Let's do some more maths. Yeah. What would a graph of net force against change in momentum look like?
Like
What about my delta T? The straight line.
A straight line. The two quantities, if delta t is a constant, say the moment of contact between the two objects is a constant, then to have a bigger change in momentum, you'll actually have to exert a bigger net force for the same time. Am I right? Are you with me?
Yes.
So the F net delta P will be a linear graph because the F net, or actually it is delta P, the change in momentum, is directly proportional to the net force acting on it, because the change in momentum will depend on, so this is my dependent, and that is my independent. So actually, in reality, I should swap these axes around. So this is the dependent variable, and that is the independent variable. And I'm very naughty by leaving the units out. I am obliged to put the units there: kilograms, meters per second.
Ma'am,
Yes.
swap them around because sometimes in safety likes to swap them around. Like, yeah, it likes to do that.
Well, in science we can do anything. It depends on what you're looking at for. If they say, I'm just trying to explain that it's the change in momentum that would depend on the net force.
Yes. Wait,
I'm waiting.
Yeah, so it's,
okay.
Hmm?
you have to copy the graph like on the right.
Both. Why not? What's wrong? They can give you any of the two.
I think you should.
Come, you're not babies anymore. I just took a second one to say this is the dependent and that's the independent, but they can ask you to draw a graph the other way, or they can give it to you the other way. Okay? You know what's coming next, no?
Yes.
What's the gradient of this graph giving us? You sure? Isn't it 1 over time?
Oh, yes, you're right.
Are you sure?
Yes,
1 over t. Because if you look at this equation,
no.
F net over delta P will give me 1 over delta t. F net over delta P will give me 1 over delta t.
Yeah.
Are you all with me?
Yes.
Okay. What is the gradient of this graph?
It is delta P. Oh, delta T, sorry.
Delta t.
Yes.
How do I get that? This is delta P over F net. So then you see this fraction swapped around to get the gradient of this graph. So that will be equal to delta t.
And now, impulse is
The product of,
no. Impulse is with a vector.
of course it's a vector.
Here is a force.
G.
It's a force times time.
Change in momentum is a vector. Impulse equals change in momentum, so it's a vector quantity. We'll talk about it again. Okay? Can I go to the next slide or must I wait? Can I move? Okay. What would a graph of F net against time look like? Nalo? What curve? Diego? A hyperbolic curve. Why do you say that?
It's because F net is inversely proportional to time.
It's inversely proportional. So F net is inversely proportional to the time. If we have delta P, the change in momentum, to be constant. So the shape of the graph is hyperbolic.
How do you know where it started?
Doesn't matter where you start, it's a sketch graph.
No, it's like, how do you be like this?
No. What's the shape of a hyperbola?
That's right.
Can't you remember from mathematics? Huh? The mathematical thing is y equals k over x, or yx is a constant. That's the hyperbolic graphs formula, the general formula, and we only work in the first quadrant, so we don't worry about the image there. We only work in the first quadrant. Are you happy? What will the graph of F net against 1 over T be? Beautiful. So F net and 1 over delta T, so it's the second to the power negative 1, am I right? That one will be linear. Yes.
What do you mean by the change of the momentum is constant?
You see, with a hyperbolic relationship, there will be two variables and one constant. Otherwise, you can't draw a hyperbolic.
So you follow the
Yes. Then, if you want the relationship between the net force and delta T, you have to keep delta P constant. Now this thing F net with a proportionality sign to 1 over T, we can express it in two ways. I can say F net is inversely proportional to delta T, Or I can say f net is directly proportional to 1 over delta t. It's two ways of saying the same thing. So if you draw a graph of f net against 1 over delta t, the two would be directly proportional. And the condition is directly proportional because delta p is not changing. Are you with me? Okay? So my question will be, of course, what is the gradient of this graph going to give me?
1 over delta p.
1 over delta p or just delta p? It will give you. You see, because the only thing that makes this thing is the delta p.
Yes. If it wasn't, if the 1 over delta t would be this change into delta t, that means, like this first block, that means the gradient is delta t, it's 1 over delta t.
Yes, this is f net over 1 over delta t. That's the gradient. It will be the change in f net over 1 over the change in time. And what is that? That's f net delta t. And what is that? Delta p. So the gradient is ultimately delta p, the change in momentum.